So after learning about the wave properties of reflection and refraction, we're moving into the last wave properties that are a result of interference of waves, okay? And that would be interference patterns and diffraction patterns. And we've already talked a little bit about how waves interfere when they overlap, when they intersect. And that was through the law of superposition, or the principle of superposition. And I know that you guys have seen this effect even in a swimming pool. If you're sitting on the edge of a swimming pool and you're creating two waves by putting your feet in and out, okay, so imagine your feet are popping in and out of the pool, generating these wave patterns. As long as they're in phase, you get an interesting overlapping effect and you create this rippling effect, okay? So if you have time today and you're in Accra and you have a pool, go sit down at the edge and try to move your legs up and down at the same time, and you'd see this interesting pattern that generates, okay? And this is called an interference pattern, a result of two waves overlapping. All right, what you would see is that you'd have regions where the water creates large amplitude waves, and then you'd have regions in space where there's no amplitude at all. It looks like there's no wave there whatsoever. You get this interesting radiating wavefront pattern. It's not equal. You get these rays that kind of pop out in different directions and regions of dead space. So why that occurs is because the waves at these regions don't overlap constructively. Here, a crest would overlap with a trough. And we can actually mathematically predict where, at what angle, these rays of dead space would appear. And we can predict where I'd get maximum amplitude. And that's what we're going to do in this lesson. Another place that you've seen interference patterns or heard interference patterns is if you have a stereo. Okay, if I have two speakers that are producing the same sound at the same phase, okay, and I stand at a certain distance, I'll find that the loudest place would be if I'm standing right in between the two speakers. And then if I move left and right, I find that the sound quality changes a little bit. I could actually go to a point where the sound quality becomes really, really bad. You'd be sitting there thinking that we need to turn up the volume, but your friend is hearing everything perfectly fine. And that's because of interference that we're going to talk about in this video. Okay, so this is an important principle if you're going to be having a nightclub or you want to create a really perfect show in a theater. You want to understand acoustics and how sound waves interfere to create a perfect experience for your audience. All right, so interference patterns are created when waves generated by two different sources intersect, and they're governed by the law or the principle of superposition. It's not a real difficult concept to understand. All right, if I just had one speaker, I'm not going to have any interference pattern generated at all, okay, because I'm only generating one wave. So if this lady walked left and right, she would hear pretty well the same intensity of sound. It might start to die off if she gets further away because the intensity of the sound is going to go down. You can see that over here. And that's based on the inverse square law that we learned in another video, okay? But if I have two sources, okay, and I walk left and right, I will hear quite a difference in sound, okay? If you look carefully here, you'll see dead spaces and you'll see spaces where you have wavefronts. So if this person walks, right in the middle, he's going to hear the loudest sound. And then we can see that there's nothing here. And then you hear some sound again, nothing here. And then the intensity of sound tends to die off as you go further left or right, okay? This is an interference pattern. The perfect place to stand would be right between the speakers, okay? And even closer would get me a larger sound, but right between the speakers, I'll get good sound. But at that point, I will have horrible sound, almost nothing at all. Okay, so if we actually had a microphone and we were recording this, we would have done this in the classroom with tuning forks. But if I had a microphone and you walked, you would see a graph showing high intensity sound and almost zero, and then high intensity and then almost zero. Okay, so how can we predict that pattern of intensity? High intensity, zero, high intensity, zero. Okay, it's simple geometry and understanding a little bit about wavelength and how far you are. Okay, so let's just take a look. If I had a speaker over here and I have another speaker over here, and each of those are generating waves. I'm just trying to draw what the interference pattern is going to look like. That's my wavelength, and the speaker below is generating the same wavelength. The point at which they intersect, okay, that would be a crest, and that would be a crest. I would have 2 times the amplitude at that point, okay? So I would have quite a large intensity of sound at that point, all right? But if I carried this forward, if I drew these crests in a little bit larger, what you're going to see is at a point over here, a crest is overlapping with a trough of the other wave. If a crest overlaps with a trough, they get cancellation. Okay, so there'll be no amplitude whatsoever. The intensity of sound wherever a crest overlaps with a trough is going to be 0. Okay, so if I want to predict, if I have a speaker, okay, if I have a speaker here and I have a speaker here, and I'm going to be standing at a point over here, and I want to predict, will the intensity of sound be high or low? I need to take a look at how the waves are reaching me, okay? Let's say that is reaching me at a trough, and that is reaching me at a crest. What do you think would happen? Would I hear a large intense sound, or would I hear no sound at all? Well, as I said, according to the principle of superposition, okay, if a crest meets a trough, we get cancellation. So there would be no sound over there. Okay? And in order to do this mathematically, what I would need to know is certain things. I would need to know the wavelength of each of the speakers. And another thing I'd need to know is path length difference. So I have a path length for that first wave, and I'll have a path length for the second wave. Okay? If my path length difference is half a wavelength. Okay, so if I added up that path length difference and it was half a wavelength difference, what do you think is going to happen? Is that going to be a constructive form of interference? Is that going to be a destructive interference? If my path length difference between those 2 points is half a wavelength, that means that a crest is going to be meeting up with a trough. Okay, so I'm going to have cancellation. The only place that I'm going to have constructive interference, where I'm going to hear a louder sound, is if my path length difference is a full wavelength. Okay, so let's just draw what that looks like. So I'm going to say n wavelengths. It could be 1 wavelength, it could be 2, it could be 3, it can be 4. But as long as the path length difference is a full wavelength, a crest is always going to be meeting up with a crest, and I'll have constructive interference, and I'll be hearing sound. Okay, so let's just take a look again. If I drew my speaker here, and I drew my speaker over here, and I'm standing over here, and let's say my wavelength is equal to 1 meter. Okay, if I am 2 meters away from that source, and I am 3 meters away from that source, will I be hearing a sound, or will I not be hearing a sound? Well, I'd have to calculate my path length difference. So my path length difference is equal to 3 meters minus 2 meters, which is equal to 1 meter, okay? And if I take a look at that 1 meter, is that 1 meter an order of magnitude of a wavelength? Yes, it is actually 1 full wavelength difference. So in that case, I'll be hearing a sound, okay, because it's constructive. Okay, we'll do a few more practice problems in the next video. But the idea here is it's pretty simple. All you have to do is figure out the path length difference between the sources. So I need to measure the path length between here and the path length between here and see if that difference in path length is on the order of a full wavelength. If it's on the order of a full wavelength, I will have constructive interference. If it's on the order of half a wavelength, I will have destructive interference.